Hello Year 9s. Today we're actually going to do modelling using linear equations. And you know, there's all sorts of examples in the text, but I've decided to do something a little bit different. This here is the Fitzroy River system. It is the largest catchment that goes to the eastern seaboard of Australia. What that means is that rain that falls in this massive area here, and you know, as a main point here, it's Rockhampton, because all the rain that falls here and goes through the river system ends up going through Rockhampton, a glorious, glorious floodplain, and out to the ocean. But this thing is huge. It actually covers 142,665 kilometres square. Nebo up here is getting close to Mackay, Claremont, heap of mining areas, Emerald, Springshaw, Rolleston, even down to Injune. I think here you're starting to get inland from Bundaberg. The point is, this is a massive river system, and all this water eventually goes through Rockhampton, which is why it floods so often. Now, in April, just leading into late March and April, May 2017, we had a major flood event. It was due to ex-tropical cyclone Debbie. We actually had school closed 2 days earlier before the holidays, if you happen to remember it, in 2017. And so naturally, I found myself in Rockhampton. Now, Rockhampton, because it's so huge, they get a massive amount of prior warning about the flood that's going to happen in Rockhampton itself. And I ended up doing some interesting and relevant mathematical analysis on this. And it ties in with what we're about to do today. So rather than do the text one, you're going to get me showing you something interesting and real world. There is a relationship between the flood level, a little earlier here on the Fitzroy, about 3 to 4 days earlier at a place called Riverslea. The river height at this place called Riverslea gives a really good indication of what the flood level will be in Rockhampton 3 to 4 days later. And so what I did is I got these data points from the big floods in Rockhampton's history, and you can see it here. And here is the peak further up the river system, so 3 to 4 days earlier in metres, this place called Riverslea, and where it peaks, compared to where it peaked in Rockhampton 3 to 4 days later, and that's also in metres. You see those dot points? They represent all the major flood points that have been recorded in European history. There's actually some really interesting stuff of that was probably happening pre-European that we don't have as well documented, that is quite fascinating. But here you can see that the biggest one was 1918 that we have recorded here, and 2011 came along to be quite close to these dot points as well. Anyway, I managed to make this model here. This model says the flood height in Rockhampton is this times the flood height in Riverslea plus a certain amount. Now you're probably going, what type of model is that? It's a linear model! So today, instead of the text examples, we're going to be using this linear model about real flood levels in a major town. What's amazing to me is look how close that line, that linear equation, comes to those data points of previous floods. It's actually amazingly close to the real world, a real linear relationship, which has quite some consequences. And that leads into the questions that you're about to get. So here we go, ladies and gentlemen. Here's the model. R represents Fitzroy River height in Rockhampton. F represents Fitzroy River height at Riverslea. By the way, I have to credit a gentleman by the name of Barry, my mate Barry, who really sucked me into getting this to work and having a good look at it. And there were quite some interesting reasons why we were looking at it at the time. There was some uncertainty in late March into early April about exactly what was going to happen with the flood levels in Rockhampton. And every few centimetres actually means more houses get water in it, and some really, really big decisions. So this stuff actually has quite some significance. I've just got to get a data value here So from my email. Where's my email? Right, so first question, mathematical. Right, the 2017 flood peak at Riversley, it ended up being 26.32 metres. What will the peak be in Rockhampton? So this is using your linear model. Alright, so the Riversley peak is represented by the letter F. So we know that F is 26.32. What we want to know is R. So we'd state our model and then we put our values into our models. R is 0.2483 times 26.32 plus 2.343. By the way, notice how things aren't always nice happy numbers. See, real world data, you get all sorts of decimal stuff in it. The gradient there, look at the gradient. The gradient is 0.2483 and the y-intercept is 2.343. Real world data isn't nice whole numbers. So I put this in my calculator, 0.2483 times 26.32 plus 2.343, and it gives me this. It gives me 8.88 if I rounded it. So approximately 8.88 metres it estimates to be the peak in Rockhampton. Now, I'm somewhat pleased to say that days later, it was 3 to 4 days later, the actual peak in Rockhampton, I don't know what it was. The actual was 8.9 metres. And they only do it to one decimal place. I personally could hack the fact that we were 2 centimetres. We were 2 centimetres off with that model to what actually happened in Rockhampton, which I thought was quite extraordinary, really, for a fairly simple linear model of a situation. Now, just a sec, I've got to grab another number. Okay, we're back. The number I wanted to get is Rockhampton has an airport, main airport servicing the town, and that airport needs to close due to flooding if the river height in Rockhampton reaches 8.7 metres. So the next sort of logical question you get with this is, at what Riversley height, because remember Riversley is 3-4 days earlier, height would you recommend Rockhampton Airport to close? Now, given that that corresponds to 8.7 at, go away cat. So at Rockhampton, the airport has to close at Rockhampton if it hits 8.7 metres. All right, so R is 8.7, and we want to know F. We want to know what height up the river would suggest, oh, we're actually going to have to shut the airport. So we put that in the formula. Again, normally I'd write the formula first, but limited space. 8.7 is equal to 0.2483 F plus 2.343. So we need to solve for F. I hope you realise from your linear, well, from your algebra generally, whatever we do to one side, we do the other. I'm going to take that 2.343 from both sides. So that gives me 8.7, subtract 2.343, gives me 6.357 equals 0.2483 F, that's still there. To get F by itself, the opposite of multiplication is division. So I now need to divide by 0.2483. So divide by 0.2483. And what it tells me is at about 25.6 meters. So if Riversley hits, and you know, you be conservative with this, you don't want to leave an airport open and then have water in it, and because that could be absolute disaster. You'd probably be conservative. You'd say, look, 25, it's definitely, you know, you'd be closing it. But yeah, the Rocky Airport will need to be closed if Riversley reaches about, you know, let's tune it down slightly, about 25.5. It's going to have to close. Right, you do it lower than that just for safety, and that's what public officials do. They take the safe path because it's not worth risking people's safety and lives. Yeah. Anyway, guys, that's an example of a real-life linear model that seems to work surprisingly well. It wouldn't work well if you had the biggest flood ever known to humanity through there, because it probably would start behaving in really unexpected ways. And it also wouldn't work well for it doesn't work well for really small levels of flooding, because there can be tidal influences, all sorts of things at lower levels. So, but this is a real world linear equation. Anyway, you can look at the examples in your text. They're things like, you know, someone wants to charge you $20 an hour and a $50 call out and stuff like that. All sorts of equations that you've seen before, but this was just something a bit different. I hope you've enjoyed the experience, and yes, go forward and use mathematics to take over the world. Cheers.